Okay, let's continue. Now we know the Reynolds number and the relative roughness factor. We can check the Moody diagram now. So let's have a look at it together. We're going to use these two numbers. Okay. This is Reynolds number. This is D over epsilon. So let's have a look at the Moody diagram. This is the Moody diagram we showed you last time. And on the bottom of the page, we know this is a Reynolds number. And 5.67 times 10 to 4. So this is the red line over here. That's the Reynolds number we just calculated. And now from there, we need to find out that D over epsilon, that is 8,400. 8,400 is in between 5,000 and 10,000. So you see this one has to be something in between these two curves. So I'm going to go through here, and find out cross on this red line, the Reynolds number we just read, and the two curves getting really close to each other. So let's zoom in. So it's somewhere over here in between. And if you go back across the line to the left side, the friction factor shows is about 0.021. Okay, so that's how we read the Moody diagram. So let's write it down here. We read F equals to 0.021 approximately. And this is from Moody's diagram. The Moody diagram. Okay, so let's go back to this Moody diagram, and if you remember, we also introduced an equation to you like this. Is a big equation. I think we wrote it down for you last time. And if you remember, in this equation, there's some constraints to use it. We can use this for turbulent flow, but the condition is it has to have a D over epsilon number larger than 100, which is this line, and smaller than 10 to the 6, so it's on the bottom there. And then the Reynolds number has to be larger than 5,000, which is this green line here, and then smaller than 10 to the 8. It's on this side. So basically what we blocked with this green pen is the zoom that you can apply this equation. Now, our point is somewhere over here, so it actually fall into the zone. So what I want to do is I want to double check this friction factor with you by using this equation. Okay, so let's come back. So we're going to double check. So check this equation. The equation is like this. I'm going to write it down again for myself. So 0.25 and then log over 3.75 D over epsilon and 5.74 over Reynolds number power of 0.9 close bracket, and all together you have to square this, so that's what we have. Now let's plug in the numbers. We have 0.25, and then this is log 1 over 3.75 times 8,400 plus 5.74, Reynolds number 56,750. and 16 and power of 0.9. Don't forget to square this, okay? And if you do the calc, and this come out with, this number is 0.02069. Okay, that's approximately 0.021 as well. So our reading in Moody diagram is very accurate. Okay, so now once we get this friction factor, we're going to use Darcy's equation. It's F L over D V squared over 2G, right? Okay. So I'm just going to use this 0.021. That's what we read in from Moody diagram. You can use the other one as well. Won't make a big difference. And the length from distance from 1 to 2 is 45 meters. And the diameter, if you remember, that is 0.0126. That's in meter. Okay. And then we have velocity, we calculated already, so this is 1.724 squared, and 2 times gravity in SI unit, 9.81. Okay, so head loss, 11.36 meter. Okay, the question is not ended yet, so the question is asking for the difference of the pressure in between 1 and 2. The pressure equals to gamma times HL, head loss. Okay, what is gamma? Gamma is the specific weight of water, and this water is at 75 degrees Celsius, right? So let's go back to this property table. Specific weight, 75 degrees Celsius, so 9.56. And the unit is kilonewton per meter cube. So let's write this down. It's 9.56 kilonewton meter cube. And then what do we have? It's HL, 11.36 meter. Okay. So what do we get? We get 108.6. And what's the unit? The unit is kilonewton per meter square, which is kilopascal. Okay. So that is the final answer of this question. Okay. So that's about this example. If you have any questions, please let me know. Have a good day. Bye now.